So I did actually get a request for two problems this morning, so I'm going to go ahead and start with those first. Both of these come for organic ones, so let me bring them up on the website. So the first question is question 17. And question 17 is the problem I threw out the first homework set. So if you're curious about question 17, this is one I disagree with. I'll bring it up for you to see. Um, I'm very confused by why the book thinks that these are hybridized the way they are. A is definitely sp3 hybridized nitrogen, and it seems to think that it's sp2 and that it's sp2 for B as well. No, nitrogen is definitely sp3 hybridized for A and sp2 hybridized for B. It's kind of one of those conservation of bonds things. So if you're curious about question 17, I just haven't gotten around to taking that off the homework set yet. The other one I got asked about, that was an easy one, was question 20. So in question 20, what is the structural formula of a compound with molecular formula C4H8 Cl2, in which none of the carbons belong to methylene groups and chlorine atoms are at a terminal end. So methylene here refers to, okay, so let me bring up the problem. So I was asking for two different structures. One where so we don't have any methylene groups, these are CH2 groups. So I'm just going to write that on the board behind me as a note to myself. And we've got one where we've got chlorine groups at the end. And we've got CH3 groups at the end. So which is write the structural formula of the compound molecular formula C4H8Cl2 in which none of the carbons belong to methylene groups. So as a first pass, I'm going to assume, since it talks about terminal ends, it's referring to linear chains. So we've got 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4. Now this one's pretty easy. We terminate with CH3. So our chemical formula is C4. We've got H8, so there's 8 hydrogens that need to be incorporated. And we've got 2 chlorines. So also for this one, it says chlorines at the end. Now, in order to get rid of these methylene groups, these extra H's, we just basically need to put double bonds into the molecule. So as a first pass, let me get rid of the 2 hydrogens that are there and the 2 hydrogens are there. So if I do this, I've got 1 hydrogen, 2, 3, 4. So we've got them at the end. We've got C4H8. And they don't belong to methylene groups, which means no CH2s. So the formula for an alkane is C4H, for C4H8 would be C4H10. So this is a saturated carbon. Because when we do the 2 Cl2s, we would replace them with the 2 hydrogens of chlorine. So this is saturated, so there's no double bonds. Chlorines are at the terminal end, and none of the carbons belong to methylene groups. So how would you get that? Four carbons. Oh, it's C4H8. Okay, I don't know. That's still correct. Okay. So let's stop assuming the chain then. And let's assume well, we're looking for terminal carbons. So this one's easy down here where the chlorines are in the center. Because if we do this, we have a CH, a CH, CH3, CH3. So that one should work. So let me draw that one first. And I'll show you my line of reasoning for the last one. So I'll solve the last one first, and let me see if I can solve the one after it. But I want a double bond. I don't want a double bond. So now we have chlorines at a, chlorine at a terminal end. Doesn't have to be at both ends. So now, if we put the chlorines on the same atom at the end, now we have two methyl groups and one methine group, and neither of these are CH2. So let's see if that works. Okay, making sure I'm still on the desktop. Wow, this editor is awful. Got them both right. So again, what was my line of reasoning? Well, the last one was easy. So I verified that this is actually a saturated hydrocarbon. So a saturated alkane is going to have a formula C4 for CnH 2n plus 2. Now, if I have any halogens, they're going to replace one hydrogen. So even though this should be C4H12 because I have two chlorines, those are basically going to look like two hydrogens. So I know there aren't any double bonds in this compound, and there aren't any rings in this compound, which means I have to be working with a linear or linear branched alkane. Now, it does give you hints. It says that there are chlorines that are on a terminal end versus chlorines that are not on terminal ends. So go ahead and start with your 4 carbons, which made the last one pretty easy. So because it says there's no methylene groups, there's no CH2 groups. So this satisfies it. Now in terms of this, if I had started out with this, I'd have 2 methylene groups, but I can make 2 methyl groups by moving the carbon over. So this is just kind of an exercise in getting you a feel for basically constitutional isomers and how you can rearrange them. All right, so any other questions in that homework set? Now, a student did send me an email. There is a book I recommend on the course website, but it's not required, and I vacillate back and forth between requiring it for future semesters and not requiring it. And the reason I bounce back and forth on it is that when I was in college and I took organic chemistry, I didn't need it. But I understood mechanistic errors and I understood lone pairs and resonance. So I just kind of had a disposition for it. For students that don't really understand lone pairs and struggle following reaction errors and reaction mechanisms, it's a really good book. It actually really does a great job of walking you through how to do lone pairs, how to do resonance structures, how to do reaction mechanisms. So you may ask, okay, well, why don't you just incorporate the notes? It is in the notes, but it's one of those things that, for me, I found that I could give you 100 homework problems. Well, some people need 100 homework problems to figure out a concept or an idea. Some students only need 2 or 3 examples and they're done. And particularly if you've had me for Chem 1, Chem 2, you see that. My homework sets are very minimalist. 5, 6 problems for concepts just so you can kind of get a self-assessment. But I have the practice packets, and that's why those are on the course website, are for people who need the additional help. So I don't believe in having like the exact problem asked 50 times on a homework set, because if you got it the first time, you're going to get it the 50th time. I don't want to waste your time understanding it. But I also understand that there's students who need the extra practice, and so there's practice packets. This book is kind of the same thing, is that we do go through a lot of examples on drawing reaction mechanisms and using mechanism arrows, and we're going to talk a lot about resonance, but I don't want to spend 2 or 3 lectures just kind of asking you the same problem over and over again, because some of you are going to get really bored, but some of you need it. Now, the Pushing Electrons book is a good book. It's actually one of the seminal texts on how to understand those types of things. It's also like 40 or 50 bucks. And that's really kind of where my hesitation comes with requiring the book, is that it is an additional financial burden for taking the course. Some of you are going to really benefit from having that $50 book. Some of you are going to be like me, where you're going to buy it and it collects dust on a bookshelf for years and years and years because you bought it, you spent the money, and you don't want to throw it away, but you never use it. So as we start progressing, if you are struggling with resonance structures, if you are struggling with understanding reaction mechanism errors, I would highly encourage you to order a copy of the book called Pushing Electrons. I think the author is Weeks. You can find it under the course entry announcement. It's also under course resources. And it's on Amazon Prime. You can get it within a couple days. So get it if you need the practice. Every student I've had who has used it said it's a very valuable book. But I've also had plenty of students take the course and not need it at all. So I bring that up because a student has asked me questions about Pushing Electrons. If you want me to answer questions from Pushing Electrons, I'm more than willing to, but my copy is out on loan right now. So if you do send me questions from that book, you're going to need to send me a photograph of the problem you're asking, because I don't have a copy of it on hand. I also have the edition I used in college, and I know that we're multiple editions away from that right now. So what may be on page 32 for me is not necessarily what's on page 32 for you, and vice versa. Again, it's a good book, but it's that $40 price tag that I don't want you to buy a book that you don't need. If it was $10, I'd totally require it, because if you throw away a $10 book, it's upsetting, but be honest with yourself. It's not that big a burden. $20 to $30 is where my price cutoff point starts to show up. All right. For those of you lurking out there, what questions do you have for me? I know we're pretty early into the test 2 material. right, no questions. I got the banjo today. I'm going to try to play it with fingers that are very tired from climbing this morning. Let's see if I can still do this. Oh, good, a question. Just want to say thank you for your helpful videos. Your video about cutlery made it easy. Oh, well, glad I helped. We really don't get to see much in terms of YouTube. We don't really get to see who's viewing our videos. I mean, we get analytics, but not much regarding that. I also find it interesting now that YouTube is like recommending people to my channel, even if they're not students. Oh, good, it's down to $23. Then I can actually recommend the book. No, it ran up to $40 for some reason, because when I was looking at updating the materials for this course, I was like, this is a fantastic book. I really wish I had like recommended it sooner, but when I saw the $40 price tag, I was like, this is ridiculous. I mean, it's like a 100-page paperback. Like, I read science fiction novels with longer books with more pages than that, and it's not like more than 10 bucks. But yeah, it's just a book that contains it really breaks it down. It starts out by making you resonance structures, gives you lots of worked examples, it makes you work through lots of examples. But again, when I saw the $40 price tag, I thought, well, that's a lot of money to pay if you don't need a resource. Because practice packets I can give you days for days and days and days, they don't cost you anything. But it is a very good textbook for teaching reaction mechanisms. So, question just got asked. I have a question on the lab report. You told me that the naphthol does not react with sodium hydroxide. Highlighted benzoic acid reaction. Yes, both of those reactions were incorrect. So that's just like a computing coding error. I just went to where I saw the first issue. So for this lab you just did for the organic 1 students who did the separation of a 3-component mixture, naphthol is not an acid, it's a base. So if you wrote that it reacted with a sodium hydroxide, that's incorrect. So that pKa there, because you were looking at the pKa, because the benzoic acid reaction is also incorrect. So if you wrote that the benzoic acid reacted with bicarbonate, that's also not correct as well. So there's 2 misconceptions I saw with the lab reports. First of all is that naphthol is an acid. So I got this a lot. During the alkoxide with H2O. Well, the thing is that we use water as a reference. So pKa of water is 7 at room temperature. Anything that has a pKa lower than water is acidic. Anything with a pKa higher than water is basic. So naphthol has a higher pKa than water. So what that means is that if you were to generate this alkoxide, the water would immediately protonate it. And you'd be back to the hydroxide. So you don't really get anything from that reaction. The other thing is that, as its name implies, benzoic acid is an acid. It reacts with bases, and sodium hydroxide is a strong base. So we would expect the benzoic acid to react with the sodium hydroxide. Now, why did I say the bicarbonate reaction? So this is the second misconception. Bicarbonate is both an acid and a base. So you can write the base reaction will write under acidic conditions to form the carbonic acid, but it will also dissociate to give you carbonate. So why do we know it's this reaction and not this reaction? Well, we have benzoic acid in solution. Excuse me. And as the name implies, benzoic acid is an acid. So that H plus here is actually going to drive this reaction backwards. So the bicarbonate actually protonates this. So instead of it being with sodium hydroxide as HCO3, we end up getting, it's not a hydronium, I forget what these are called, but we get this complex instead. We protonate the alcohol, and then we add the hydroxide later on to remove out the benzoic acid as a carboxylate ion. So the reason I highlighted the benzoic reaction was that it's just chronologically the way you remove them. So you add the bicarbonate first, and the claim in the lab report was like, well, add the bicarbonate, the benzoic acid is like, both of those reactions are incorrect. That's not what's going on. Benzoic acid is an acid, but it's not an acid like HCl. It's not a strong acid, it's a weak acid. So if anything's going to deprotonate in solution, it's going to be your carbonic acid here. This is going to lose a proton before the benzoic acid does. And that's why we need a strong base. But I definitely saw this a lot. I was concerned by this because I know we talked about it in the lab, that alcohols are not acids. They don't lose their hydrogens. They can, and there is a lab that I want to do in Organic 2. I want to move it to Organic 1, where you're going to basically look at the properties of alcohol. But to drive this type of reaction where you remove a hydrogen, you'd have something like sodium metal. I'm sorry, not sodium plus. You have to have sodium metal because it removes the hydrogen as removes the H plus as hydrogen gas H2. But yes, naphthol is not an acid. It doesn't ever act like an acid. So a lot of students made this claim that benzoic acid removes the bicarbonate as CO2. You didn't see any CO2 form. You didn't see any bubbles. So yes, the question just is it flipped? Yes, you flipped the reaction. So actually the benzoic acid crashed out with the sodium hydroxide solution, and the naphthol crashed out with the bicarbonate solution. Now if I remember correctly, the bicarbonate came first. So solution A was the naphthol and solution B was the benzoic acid, but people had those flipped because they were treating naphthol as an acid. And they were claiming that the benzoic acid reacted with the bicarbonate, and again, I saw claims that will produce the CO2. It was like, but you didn't see any. So if you look at the reaction of vinegar and bicarbonate, you see the CO2 when you form it. It's not a subtle reaction. So if you add benzoic acid to bicarbonate, you don't see any CO2, then that's not what happened. You would see it bubble, you would see it fizz. But yeah, in a lot of lab reports, I saw that A and B were flipped. And everything that follows from there is incorrect. I mean, the dimethoxybenzene, everyone should have gotten that one right. But definitely if you flip A and B, then your percent recoveries are incorrect for benzoic acid and the naphthol. Other questions? It's a gas, right? If you so comic just got asked CO2 and be observable. You see this when you open up a soda, like the CO2 comes crashing out. So the solubility of CO2 in water is not high. That's why your bottles of soda have to be under high pressure. But the CO2, in order for it to, if you're going to form it, it's going to bubble out of solution. This is actually a great reason. This is a big reason why we use carbonate salts. Oh, hi. Carbonate salts to figure out if we've neutralized reaction. So when we neutralize acids and bases, we like to use bicarbonate because it'll stop fizzing when we're going to say neutralize, really, it'll do it all the way up to a fairly high pH. But if you were shaking it, you're just going to, if you shake any liquid, you're going to get some foaming. The bigger question is that when you mix them together, did you see like effervescence? Did you see like if you threw, God, what's that stuff? It's Alka-Seltzer. If you throw Alka-Seltzer in water, you see that type of bubbling. That same thing would be true for bicarbonate reacting with an acid. It bubbles out. So while we got it up, let's talk about pKa bicarbonate. So I'm looking at the pKa benzoic acid is 4.2. Why won't you show me this? Bicarbonate. So, I'm sorry, I missed the question from earlier. So, the naphthol is a base that reacted with a weaker base. Bicarbonate is not a base, it acts both as an acid and a base. So, naphthol, a base, reacted with a weak acid. This HCO3 here is a weak acid. Now, bicarbonate's one of those ones, it straddles the line. So its parent acid, the carbonic acid H2CO3, is a diprotic acid. It can produce up to 2 protons on reaction or on dissociation. So again, bicarbonate here is not, it can act as a base, but it can also act as an acid, and that's what it did in this case. Well, it's only that part though. So you do need to go change the reactions. That's going to change your results, but it's not like you're radically rewriting your whole lab report. So this lab did kind of come early. This is more like a third or fourth week kind of lab. Definitely not second week of semester. So at that point, we would have had a bit more time to talk about functional groups, a bit more time for you to get comfortable with it. So in terms of the points I've been taking off for that, I think it's been roughly 7.5 points for if those reactions are flipped. I think that's pretty generous. On the one hand, you're not kind of at a point where you would have necessarily known that alcohols don't act like acids. So I answer the other question first. But on the other hand, we did talk about it in lab. Like we actually went through which ones are going to be which. So if we were late in the semester, I probably would have done 10 points for it because yeah, everything that follows from there is incorrect. 7.5 points seemed like a reasonable distance. So other question, did you already explain why the bicarbonate would have chosen to react first with the naphthol over the benzoic acid? Because it can react with benzoic too, right? In principle, it could. It could accept a hydrogen from the bicarbonate could accept a hydrogen from the benzoic acid, give you the carbonic acid. Honestly, if you're really clever in terms of your error analysis, this would be something good to bring up. That benzoic acid is a weak acid. It principle could have formed bicarbonate or could have formed the carbonic acid, and that would have left you with the benzoic ion. So probably some benzoic acid did crash out with the naphthol. Because we don't make you do a TLC of these materials, you don't know for sure that you truly extracted it. So yes, there is going to be some cross contamination of the naphthol with the benzoic acid, and also vice versa. Not all the naphthol, because naphthol is a weak base, not a strong base. Some of it would have still been left in the organic phase and probably would have crashed out when you put the sodium hydroxide in there because, again, it can accept, I don't have it up there anymore, it can accept some hydrogens from the water, even if there's not a lot of them up there. But as far as why it chooses to react with the naphthol over the benzoic acid, let me look up the pKb of. So I'm looking at the pK of bicarbonate. So the pKa here is, first reference I have has 6.4. And then if we look at the pKb naphthol, this is going to be 14 minus 9.1, 4.49. So this is more acidic than this is basic, so it makes sense to say that if this is going to donate a proton, it's probably going to be a good enough proton donor that it's going to force those protons onto the naphthol. So again, to answer your question, it's kind of nuanced. We expect this reaction to predominantly occur where it gives up its hydrogen to naphthol, but benzoic acid is definitely a weak acid. Now the other thing is that because it is a weak acid, if we chunk a whole bunch of bicarbonate in there and it acidifies the solution, then in principle the benzoic acid is going to be forced to stay as benzoic acid, not the carboxylic ion, and it's also going to protonate the naphthol to give you the ion. But with all organic chemistry, we're going to end up with kind of like, unlike Chem 1 and Chem 2, where we had pretty straightforward pure reactions, most likely what came out the other end, the naphthol you extracted, the benzoic acid you extracted, and even the dimethoxybenzene probably were not pure. There is a version of this lab where you would actually go through and find the melting point. My issue is that sorry, saw a quick email. My issue is that you just don't have the time to go do that. So to do 3 melting points would easily take you an hour and a half. Any other questions? You're welcome. I mean, organic chemistry is dirty. That's why you need to do characterization and analysis. Again, like this is the big contrast between general chemistry and organic chemistry. And something I wish I had more time to talk about in chemistry too would be the idea of what are called side products and side reactions. And we even kind of allude to it in chemistry too about how when we introduce the common ion effect that no equilibrium is ever in isolation. And while it's nice to talk about equilibrium reactions in chemistry too and talk about how we can solve them using quadratic equations and solvers and things like that, the reality is that with any given reaction, there's probably dozens of equilibriums going on. We've got the dissociation of the bicarbonate, we've got the protonation of the bicarbonate by water, we've got the benzoic acid dissociation, we've got the naphthol accepting a hydrogen, and we've got water equilibrium. All of those 5 reactions are going on. So in Orgo 2, we begin to see where we kind of get these dirty side products, that there is a reason why we're teaching you purification. So with the separation of a 3-component mixture, the whole purpose of that is to purify your mixture, but you can already kind of see in this discussion how even to purify the mixture, we would have to do this several times to truly and honestly get good purity. And for the stuff that you isolated that wasn't soaking wet, like you lost a good chunk of your material just to the separation process. And this is the trade-off we're going to see, particularly as you start moving into your own synthesis problems, that yeah, you're going to have low yields. Now, in Chemistry 1, Chemistry 2, some instructors grade on yields, and they say, well, you need to be getting this yield. And when I teach Chemistry 1 and we do the reaction of copper, you start with a gram of copper, you should finish with a gram of copper, and students get like 40% back, and they're like, well, that was terrible. It's like, well, you did 5 reactions, so if you lose 10% each time, you'll be down to 50%. Orgo is kind of the same way. Can you go over how to convert cycloalkanes into the chair 2D projections? Wow, somebody's really far ahead in the material. So, cycloalkanes. Specifically, when we're talking about the chair conformations and the projections, you're focusing mostly on the cyclohexane. The reason being is that cyclohexane is big enough that it can get into these chair conformations. So if I do something like cyclobutane, you can see where my model's struggling. It can only be planar. If we go to cyclopentane, we can do planar. We can also pick up one face. We can do this skewed back. But it's kind of limited in what it can do because of this bond angle that you'd associate with a pentagram. Now, if we go to hexagram, I think that's what it's called. Anyway, 6-sided object. We actually start getting bond angles that are comparable to what you would expect to see for tetrahedral atoms. So there are multiple conformations of cyclohexane. So when we draw cyclohexane, we draw it like this, and stereoscopically that means that we're drawing it as a flat image. So we would take our model and we would crush it down into a flat plane. Let's see if I can do that here. My modeling kit's getting stubborn in its old age. So if we crushed it down until it was flat. So it looked sort of like this, where it's one plane. That's what I have drawn, but that's not the reality. So there are a few ways that we can draw. There are a few conformations of cyclohexane that actually exist naturally. This planar thing does not exist at all, or if it does, it's vanishingly small. But 2 common ones are your boat. So you've got 2 ends of the ring picked up, and then you've got the chair conformation, and this is actually the most stable because it's going to put, if we look at the, not Fisher projections, the Newman projections, this Newman projection puts everything gauche. So if they're going to be forced to be like this, all the hydrogens are gauche to one another, and all the adjacent carbon groups are gauche to one another. So you see that 60-degree angle between the front carbon and the back carbon. So how does this translate into a 2D projection? Actually, this is surprisingly intuitive if you can see it. Now, the if being the statement here. So the way the 2D projection works for the chair conformation is you're going to draw this shape, which seems like a completely arbitrary shape, but if you look down, let's see if I can get it to work for you. If you were to take this molecule, I'm going to try to rotate it. You can kind of see it behind me on the board. We've got the two parallel sides. We've got the one atom down in the back, so you see that dip, my pointer's pointing right there. We've got the one atom that's up, it's that atom there. This is basically the structure if you projected a light onto this structure at an angle. So the way I view it, and I've been able to find two different ways of looking at it. These are the two sides of the chair. So if we're looking at the chair conformation, this line and this line are these two sides, arms on the chair. This is the carbon that's up and this is the carbon down. Now, I've also seen books argue that this is the part of the chair that's up, this is the part of the chair that goes down, and these are the two arms of the chair. Honestly, it's going to give you the exact same answer. The way I define it is that this is the part of the chair that's up, that's the part of the chair that's down, and these are the two arms of the chair. So how do we draw it? Well, we have to identify axial and equatorial atoms. So axial go up and down, and they alternate up, down, up, down, up, down, up, down in the drawing. Now, equatorial, some books will draw these at angles. I don't see the point to it. But equatorial, I draw is going off to the sides. So where does this definition of axial and equatorial come from? Well, axial, as the name implies, is along an axis, specifically the z-axis. So if we have our cyclohexane, our axial atoms, draw it better, the ones in blue, are the ones that are in the face, basically would look like they're in the face of the ring, and then the equatorial are the ones that stick out to the side. So your equatorial ones here shoot out. So to figure out which ones are axial and equatorial in the chair conformation, there's 6 of each. 2, 3, 4, 5, 6. So if you look at your chair conformation, you put it down on a table. There are 3 that touch your table. Those 3 are axial positions. So they're the 3 that your chair sits on. If I flip it over and do it to the other side, those are the other 3 it sits on. And so these atoms that you see going up and down, these are the axial atoms. Now, the equatorial are the ones that kind of shoot off from the side, and we call them equatorial because if these form a z-axis, these kind of shoot off at the equator of the molecule. Now, what makes this really obnoxious is that chair conformation can undergo interconversion. So if I take one side of the molecule and turn it around, come on, do your thing, these end up all becoming equatorial. So when we talk about axial and equatorial, we don't necessarily talk about them as hard and fast so much as that when you convert a flat 2-dimensional drawing to your 3-dimensional drawing, some will be both axial or both equatorial, and some positions will both be equatorial and will be axial. So how do we figure out which one's which? Well, we build up the pattern. So here I've got a 1,2-dimethyl cyclohexane. Here I have a 1,2-dimethyl, but this is going to be the cis, this is going to be the trans, cis and trans. Now cis and trans are defined using the basically the two-dimensional form of the ring, so a planar version of the ring. And they're cis if they're on the same face of the ring, they're trans if they're on opposite sides of the ring. If you built it as a chair, it would be really hard to see those. So again, for cis and trans, we're just going to look at them. We're going to pretend that the ring is planar, and then look at whether or not they're on the same side of the ring or not. Now, let's figure out which way they go. So I've got my planar ring, and I've got two atoms. In this case, I'm going to have red and white. So I built my model, it's planar, and I've got red and white, and on this board I'm going to define them that way. Where did my pin go? Oh, there you are. So I'm going to make the red one the second one. So now if I take my model and I bend it into the chair conformation, I'm going to make this the top of the chair. So this is my reference point. Sorry, this is going to get a little cramped. I should probably do it in red to make it a little bit easier. Nah, we'll do it in blue. So now let's take my planar molecule. I'm going to take it, and I want to do it with the chair conformation. So I'm going to take the white atom, I'm going to lift it up, and the atom that's directly across from the ring, I'm going to put it down. And if I look at it, now my white atom is axial. And if I look at my red atom, now it's equatorial. So it's not sitting up and down. The next carbon is down, or the hydrogen's down, the equatorial goes out to the side. So this tells me that if they're cis in the 1,2 position, one's going to be axial, one's going to be equatorial. And because we have this ring flipping where axial and equatorial flip, and they all flip at the same time, we're just going to have one axial, one equatorial. Now let's go back to the flat model. And this time we're going to have them trans. We're going to have opposite sides of the ring. And when I bend the ring to get it back, now they're both axial. So my lead carbon is up, and my next one is down. So if they are cis-trans and they are 1,2, 1,2, if they're cis, they're going to end up being on opposite axial equatorial. Now, that's the only thing that we can say is true. They're both going to be axial. One's going to be axial, one's going to be equatorial. If they're trans, one's going to be equatorial. They're both going to be axial or both be equatorial. The reason why we're not going to say that one is axial, one is definitely axial, and one is definitely equatorial is because the reason why I'm not going to say like the red atom is always equatorial is because we get this ring flipping. The only thing we can say is that in the cis for the 1,2, they occupy opposite sides. Either one's axial or equatorial or vice versa. And the trans are both axial or both equatorial. Now, when we flip to the 1,3, if we do the cis, and already wants to pop into that ring conformation, we see that they're both now axial atoms. So you get one axial and the other axial going up. Now, they are both axial and they are both on the same side. In this case, when they're both axial, one's axial up and one's axial down. If we switch to the cis, we get that one is axial and one is equatorial. So what can we say about this? Because these are separated by 1, 3, 1, 3. So this is kind of the complicated long answer, but it comes from basically messing with this model as we go around. So we're going to talk about it relative to an anchor carbon, the number 1 carbon. So if we have a group that is on the 2 or 4 position versus the 3 position. So 2, 3, and 4. And reason why we're not going to worry about 5 and 6, that's just a rotation axis. If it's on the 3rd carbon, and if it's cis versus trans, and then for the 2, 4, if it's 2 versus 4, it's cis versus trans, cis versus trans. We'll start with the 2 position. If they are both cis, then there's going to be one equatorial, one axial. If they're trans, they're going to be both axial or equatorial. And if they're axial, they're going to be on opposite sides. But when we do this chair conformation, we kind of already see that. We alternate the axial. So one up, one down, one up, one down, one up, one down. If we have 2, 4 and they're cis, they're both axial or equatorial, but because the 1, 2, 3, 4, 1, so up, down, up, down. Again, if they're both axial, they're going to be on opposite sides. If they're trans, you're going to have one axial, one equatorial. Am I saying that right? Make sure that's right. No, sorry, I got them flipped. So 1, 2, 3, 4. They're trans, they're cis. They're one equatorial, one axial. If they're trans, they're both axial. And if they're both axial, they're on opposite sides. The 1, 3, this is going to flip. So if they're cis, they're both axial or equatorial, and they're axial on the same side. If they're trans, there's one axial and one equatorial. So this is how we take the 3D drawing and we convert it to the 2D drawing. So figure out where they are relative to one another. Figure out if they're going to be axial or equatorial relative to each other. Again, there is interconversion, so it doesn't matter if they're both axial or both equatorial. This is only going to be reflected in terms of stability. But their relative positions to each other needs to be done. Needs to be correct. And I realize that was a lot of information. We are probably not to that point till next week. But that's kind of how you do it. The other thing I would recommend, build the model. So again, I can take any planar ring, make them cis or trans, and then I just have to take one side, bend it one way, the completely opposite carbon, bend it the other way, and then I can draw what I see. Anything on the edge of the ring is going to be equatorial, anything up, down is going to be axial. Yeah, that's usually something we would cover in like a whole 40, 50-minute lecture. All right, any questions before we finish up today? If you want to, next Friday we can work examples of the chair 2D projections. Yeah, it's next week, September 21st to the 25th. That's when we're going to start going through different conformations of cyclohexane, cyclopentane, cyclobutane, and the cis trans EZ notation for those. So for those of you who just watched the live stream and freaked out, don't worry, you're not supposed to know that until next week. This week you're going to focus on naming linear branched and cyclic alkanes. And the R and the S is in there. It's just not, it's daunting, but you should already know how to do it. We're just adding on the fact that now you can name where the positions are. All right, if there are no other questions, I'll go ahead and sign off for today. Thank you all for showing up today. Again, if you have any questions, please feel free to ask them. If you can't make it a live stream, just shoot me an email and I'll take care of it at the start of lectures.